All right, welcome to today's physics video. Today we're going to be learning about Newton's third law. All right, we're basically going to get the basics. That was a bad sentence. By the end of this video, you should be able to do these three things here. Given the interaction between two objects, you should be able to describe the action and the reaction forces. You ought to be able to draw that interaction, and finally you should be able to understand why the action and reaction forces don't cancel. Okay, so here we go. So before we learn about Newton's third law, I need to emphasize a really important fact about forces, and I know we've talked about this in class. So specifically, every force in the entire universe has two objects associated with it. All right, there is the object that is being pushed or pulled, which when you make your free body diagram, that is the object that you draw, right? Okay, and then secondly, there's the object that's doing the physical pushing or pulling, all right? So when you make your free body diagram, that's how you label the object, all right? So a simple example would be, if Roy pushes a box, I'm gonna draw the box, that's the object being pushed, and then I'm gonna label it force of Roy, because that's the object doing the pushing, okay? So when you make a free body diagram, we are always interested in the object that is being pushed or pulled, all right? And it is super duper mega crazy important that you understand that, that distinction. Okay, so in order to get to Newton's third law, I'm going to do a real quick demo here, and hopefully this will work here with the camera. Okay, so I'm going to go over and stand over by the filing cabinet. Okay, so here I go. All right. So right now I'm standing on this skateboard and I am not moving, right? So right now my velocity is 0, my velocity is constant because nothing's pushing me. All right, now in order to get my velocity to change, I have to have something push me, right? Because an object at rest stays at rest, right? So right now the net force on me is 0, I'm not moving, my velocity is constant. Okay, so I want to get myself moving. All right, so what I'm going to do is I'm going to push the filing cabinet. And now I'm moving, right? Okay, so my velocity just changed. It changed from 0 to not 0. Okay, so let's think about what just happened there. All right, so what happened was, here was our filing cabinet sitting on the ground, and here's me. Hello. Standing on a skateboard. All right, now the purpose of the skateboard is it symbolizes it represents there being no friction. Okay. So let's think about what just happened here. So my velocity initially was 0, right? So then what happened? Well, I pushed the filing cabinet. So if I was going to draw that, this is the filing cabinet, right? Filing cabinet. And I pushed it, right? So this is the force of Hecker. But somehow I moved, which is a little confusing to me, right? Because this force, the force of me pushing the filing cabinet, is exactly that. It's a force on the cabinet. That's a force that should affect the motion of the cabinet. But the cabinet didn't move. And the reason the cabinet didn't move is twofold. One, there's a lot of friction between the cabinet and the floor, right? Because it's heavy, large normal force, therefore a lot of friction, so it doesn't move. Secondly, even if there wasn't friction, there's a wall behind it, right? So there's another force on this filing cabinet that cancels it out. So let's just label this force from the wall. All right, and so the net force on the filing cabinet is 0. But somehow, so that's the filing cabinet. But somehow I moved, right? There must have been a force on me. And the only thing that I can think of that possibly could have exerted that force is the cabinet. That's the only thing I was touching. All right? And so what we're seeing here is that there's an interaction, all right? What produced my motion was the interaction between me and the filing cabinet. And there are two forces. There's the force of Mr. Hecker pushing the filing cabinet, which in this instance we're going to end up calling our action force, all right? Since I moved, though, there must have also been a force on me. And the only thing that I can think of that possibly could have pushed me is that filing cabinet. So there must have been a force from the filing cabinet pushing me. And as a result, my net force is equal to whatever this force from the filing cabinet is, right? Okay, and that produced an acceleration and changed my velocity to make me move this way. Okay? So, that is the deal, all right? So let's see if we can come up with a way to say this in words, all right? So here's Newton's third law. Newton's third law says the following. It says, for every action force, there is an equal and opposite reaction force. All right? In simplified terms, it's this. Anytime object A pushes or pulls object B, there's another force too, and that force is that object B will push or pull object A with an equal amount of force in the opposite direction. Okay? So these two forces, the force of A pushing B and the force of B pushing A, or pulling, is called an action-reaction pair. Okay? Action-reaction pair. Okay? I will begin abbreviating action, AXN, and reaction is RXN. Okay? All right, so this is huge. Anytime two objects come into contact, they exert equal forces on each other in the opposite direction. Okay? So, to super simplify this, it's this. If you have an action force, and that action force is object A pushes object B in a certain direction, then your reaction force is going to be object B pushes object A, pushes object A in the opposite direction. Okay? And so some important things to be aware of. First of all, in order for this to make any sense, this is going to sound silly, but your two objects have to be objects, right? Remember, I said that any force in the universe has two objects associated with it, and you have to identify what the objects are, which usually is simple, but sometimes not obvious. All right? Second thing to be aware of. If your action force is a push, then your reaction force is a push. If your action force is a pull, then your reaction force is a pull. All right? Next, the action and the reaction occur simultaneously. Okay? So in that example back here, when I was pushing the filing cabinet, the idea is my hands were on the filing cabinet, right? So there was a time during which my hand was pushing the cabinet, and during that same time, the cabinet was pushing me. Okay? This is not cause and effect. It's not I punch you and then you punch me back. All right? The action and the reaction occur simultaneously. And for that reason, the words action and reaction are a little misleading, and so it doesn't really matter which one you call the action and which one you call the reaction. Okay? Now, a lot of times there's going to be sort of an intuitive way of describing it where it feels like Hecker pushing the cabinet should be the reaction, or sorry, Hecker pushing the cabinet should be the action, and the cabinet pushing Hecker should be the reaction, but it honestly doesn't matter at all. Okay? What is more important is that you recognize that the two forces are equal and opposite. Okay? So, cool. There's a common question I get at this point. I guess let me address this real quick. So one of the common questions I get is, well, if that's true, why don't all forces cancel and prevent all motion? Okay? So we'll get there in a minute, but hold tight on that question if that's what's bothering you right now, okay? All right. All right, so the first thing that I want to make sure that you're able to do is identify the action and the reaction forces in any interaction. Okay? Doing this requires that you're able to identify the two objects and then write out a statement that looks like object A pushes object B in a certain direction and object B pushes object A in a certain direction. Okay? So there's a bunch of examples up here. So our first example is Carl pushes a box. So the first thing you have to do is identify the two objects. All right? So Carl and the box are the two objects here, right? So our action is pretty straightforward here, okay? Our action is going to be Carl pushes the box, and then you need to pick a direction. So let's just assume he's pushing it forward. Okay? So then to find your reaction, you just flip the two objects. So instead of Carl pushing the box, your reaction is the box pushes Carl backward. Okay? And so your drawing should look like this. Here's your box. Here's the force of Carl. Here's Carl. Here's the force of the box. Okay? So, this drawing sort of alludes to the fact, answers the question I posed a minute ago as to why these two forces don't cancel. All right, there are two forces in this drawing, right? There's the force of Carl, and there's the force of the box. All right, the reason those two forces don't cancel, and I'll write this down in a minute, but the reason those two forces don't cancel is because they act on different objects. All right, this force, the force of Carl, that's a force that affects the box, right? And this force, the force of the box, that's a force that affects Carl. Okay? So there's no way these two forces could possibly cancel. All right? If we somehow had a scenario where we had a box and maybe Carl pulls the box this way and maybe Dave pushes the box this way, these forces can cancel because both of those forces act on the box. But with an action-reaction pair, the forces never act on the same object, right? Because the wording is, if A pushes B, that's a force on B, then B pushes A, that's a force on A. So action-reaction forces never, ever, 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 ever cancel because the action-reaction forces act on different objects. Okay? All right, so in this next example, a table prevents a box from falling. So the idea is gravity's pulling the box down, but the table's holding it up. So my action is going to be table pushes the box up, and a reaction then, you just switch the objects, right? Box pushes table down. Okay, and then your drawing is going to look like this. Here's your table, here's your box, here's the force of the table pushing the box. Well, let me do this. Here's the force of the box pushing the table down, right? Okay. All right, let's see. A ceiling prevents a helium balloon from floating away. So let's think about this one. I'm going to draw it first, actually, this time. So let's see. So we need a ceiling and a helium balloon. So the balloon wants to float up, but the ceiling is pushing it down. So there's the downward force from the ceiling pushing the balloon. And the reaction is the balloon pushes the ceiling up, right? Okay, so let's see. My action is ceiling pushes balloon down. And then my reaction, you switch the two objects. So it's the balloon pushes ceiling up. Cool? All right. Shoot, and I'm realizing now that all of these examples are pushes. I'm kind of wishing I'd done an example with a pull. I'm pretty sure there's one on the next slide. But regardless, here's what I want to point out real quick is this, that remember, if your action is a push, so is your reaction. If your action is a pull, so is your reaction. So it happens that these were all pushes, right? Carl pushed the box pushes Carl. Table pushes, box pushes, ceiling pushes, balloon pushes. All right, I'm hoping on the next slide there's a pull, and if not, I'll make sure that I do one. All right, now, this next example, this is the one that people always, always, always struggle with on tests and whatnot. All right, so let's take a minute and do this one. All right, so it says a ball falls off a roof. So we're talking about a ball falling. So what force is being described here? The roof doesn't have anything to do with this, right? We're interested in the ball. Why is the ball falling? Oh, it's falling because of gravity, right? So this problem is talking about the force of gravity pulling the object down. So here's the common mistake people do. Do not write this down, okay? Unless you want to write it down and then write down that it's wrong, okay? Students always write this. They'll write, oh, well, gravity pulls the ball down, right? So I agree that that is an action force. But then your reaction would then be, oh, well, that means that the ball pulls gravity up? That doesn't make sense, right? And the reason that doesn't make sense is because gravity, I don't know why I said that like that, because gravity is not an object, all right? So we need to attribute that gravity to an object. So what is that? When we talk about if I take a ball or a duck, because I happen to have a duck here, and I drop it, that was pulled down by the gravity of the Earth, okay? So that gives us this then. So it turns out that the action here is this. It's the Earth. I guess technically if you wanted to, you could say the Earth's gravity pulls the ball down, but it's the Earth pulling the ball down. Let's write Earth's gravity. I like that better. All right, and then the reaction, weirdly, is the ball's gravity pulls the Earth up. Oops, I just stepped on a duck. All right, so this is weird. So here's what I'm telling you. So here's my ball. Oh, I don't know why I labeled. Erase that. I'm going to put that back. This is the force of gravity. It's also the force of the Earth. All right? So now here's the Earth. All right, so here's the deal. Gravitation is an attraction between two masses. Any two objects that have mass are pulled together by this gravitational force of attraction. Much in the same way that if I take two magnets, gravity pulls the two magnets together. Okay? I'm sorry. Try that again. If I take two magnets, the magnetism pulls the two magnets together. Okay? And usually when you do that, your two magnets have approximately the same size. So if you let them go, they both kind of move, you know, the same amount, right? Okay? Well, here, my ball and my Earth are sort of like magnets, except that the Earth is a really, 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 really big magnet. Okay? But they exert equal forces on each other. So the idea is the Earth's gravity pulls the ball down, and weirdly, the ball's gravity pulls the Earth up. So I'm going to label this as the force of the ball. Okay? But remember, force of gravity is the same as weight. So let's suppose that the ball weighs, I don't know, whatever, 10 newtons. Who cares? All right? Oh, well, that means then that my reaction force from the ball pulling the Earth should also be 10 newtons, right? Except the ball's force is up. This one should be down, so it's negative. All right? So imagine a rope is tied to the Earth, and you pull up on it with a force of 10 newtons. Well, it's not going to move, right? Let's pretend that this was the only force on the Earth. All right? Acceleration is net force over mass. So I'm going to pull with a net force of 10 newtons on the Earth divided by the Earth's mass. The mass of the Earth is this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22 kilograms. All right? So, technically speaking, if you, you know, sit in a tree and drop a 10 Newton ball down towards the Earth, as the ball is falling, the ball is pulling the Earth up with this acceleration. Okay? So technically speaking, you move the Earth every time you drop something. All right? But the acceleration that it experiences, because it has so much mass, it has so much inertia, the acceleration it experiences is virtually non-existent. Okay? So we'll talk more about that in class. All right? But at this point, what you need to understand is this. This force of gravitational attraction is mutual. All right? So when the Earth's gravity pulls an object down, that object's gravity pulls the Earth up, okay, with an equal amount of force. Equal amount of force, all right? That's the other thing I haven't been stressing yet, is that all of these examples, remember, Newton's third law says for every action force, there's an equal and opposite reaction force. So all of these forces are equal. Carl's force is equal to the box's force. The table's force is equal to the box's force. The ceiling's force is equal to the balloon's force, etc. Okay? All right. Baseball player slides to a stop. So let's see. So here's the ground, here's the baseball player. Let's have the baseball player running this way. Okay, so here he is, he's sliding into base. He's going to slide feet first. All right, so the idea is he's sliding forwards, and the thing that stops him is friction. Okay, but friction is, again, not an object. So where does that come from? Oh, it comes from the ground or the Earth, right? Whatever the object is sliding across, in this case, the Earth. All right? And then, so the reaction then would be that the player is pushing the Earth forward. So here's the force of the player. All right? So my action is Earth or ground or whatever pushes the player backward to stop his forward motion. And as a result, the player pushes the Earth forward. Okay? That's why there's, you know, he's sort of going to push dust and stuff up, right, as he pushes the dirt forwards. Okay? These are all pushes. I get an F- for writing these examples. Okay, Roy takes a step forward. So I think I talked about this a little bit in the friction video, but so when you step, you're pushing backwards on the ground, right? Look, right? So the action is you push the ground backwards, and the reaction is the ground pushes you forward. So Roy pushes the Earth backward, and the reaction is the Earth pushes Roy forward. And this only works because of friction, right? Because if there was no friction, your foot would just slide and you wouldn't push, much like trying to walk on a frozen frozen pond or something. All right, goalie stops a ball. I'm not going to write this one out. So that one's the ball pushes the goalie backwards, and the goalie pushes the ball forward. Okay, magnet sticks to a filing cabinet, so the filing cabinet's going to pull the magnet's going to pull the filing cabinet. All right, let's do another example. Let's do pulling a bucket up out of a well, okay? So in that example, it would be Roy pulls the bucket up, right? Pulling the bucket up, and the reaction is the bucket's going to pull him down. So the bucket pulls Roy down, all right? The big thing I want you to be aware of here is they're both poles, right? Okay, so that's the deal. All right, so let's do two examples. So the first example, we're going to have Roy and Sally standing on frictionless skateboards. Okay, so let's draw this. So here's Roy, frictionless skateboard. Mass of Roy is 80 kilograms. All right, over here we'll draw in blue. Here's Sally. Excuse me, mass of Sally is 60 kilograms, okay? Sally pushes Roy with a force of 960 newtons, so that's my action force. Here's the force of Sally, 960 newtons. And the way I have it drawn, this is negative. So that's kind of my action force, right? That's the force of Sally pushing Roy. Well, there's necessarily a reaction force. Oops. There's a reaction force. That's the force of Roy pushing Sally with positive 960 newtons. All right, so again, these forces do not cancel because one of the forces affects Roy, the other force affects Sally. All right, so let's find the acceleration of our two people here. All right, so the acceleration of Roy is going to be the net force on Roy divided by his mass. So 960 newtons negative divided by his mass, 80 kilograms. Divide this out and it gives you negative 12 meters a second squared. Okay, now let's do the same thing over here for Sally. I didn't quite leave myself enough room. Acceleration of Sally is the net force on Sally divided by her mass. Oops, I forgot to put an R over here on Roy. So her net force is positive 960 newtons, but her mass is only 60 kilograms. So when I divide this out, it gives me 16 meters a second squared. All right, so if we ignore our negatives, who's got the bigger acceleration? Sally does, right? Because she has less inertia. She has less mass, right? So the idea is both people in this example have the same net force acting on them, right? For Sally, that net force is seen as a small amount of mass with a large acceleration. And for Roy, we have a large mass with a small acceleration, right? But the net forces are equal, okay? All right? Okay. We already talked about why those two forces don't cancel. All right, so I don't know that I need to do this example. I'm gonna hold off on this example. I don't think it's that important right now. But the one thing I do want to say that I have not stressed yet is this. I think a lot of times students look at this and they go, oh, Sally's going to move more, so she has more force on her. And that's not right. Remember, Newton's third law tells us that the action force and the reaction force are equal and opposite. Anytime two objects interact with each other, the amount of force they exert on each other is always equal, without exception. Okay, the classic physics problem is a truck is driving down the street and it hits a bee or a bug or something. Okay, the force that the bug exerts on the truck is the same as the force the truck exerts on the bug. Okay, the only difference is that the bug is more affected by the collision because it has a smaller mass. Okay, but the forces are equal. All right, anytime two objects come into contact, they exert equal forces on each other. All right, cool. So why don't we do this? Let me embiggen this. Why don't you guys do this example on your own? And we'll talk about it in class at the start of the hour tomorrow, if you guys remind me, because I always forget to do this. So remind me to go over this example, all right? Okay, that is that.